let's take a look at a special case. I had mentioned earlier that we needed our constant c to be greater than 0 for the steps that we took earlier to work. Here's what happens if we have c, our constant, less than 0. In this case, it is a -2. Notice that we say that the absolute value of 8x minus 1 is less than -2. So remember that less than is an and. But here's what you have to remember. An absolute value always has an output that is positive. So it's not possible for an absolute value to ever be less than -2 or less than any negative number, as a matter of fact. So an absolute value will never be negative. Positive numbers, because this absolute value here has to output a positive number, is always going to be bigger than a negative. It's never going to be less than a negative. So what does that mean in this situation? No solution. There is no possible solution for x that will return a value, because an absolute value can't be less than a negative number. Let's look at the opposite of our last case. This time we have the absolute value of 10 minus m is greater than -2. So greater is an or case. However, we need to also think, wait, c is a negative number. What do we do with this -2? Now, think about this for a minute. An absolute value always has to be positive. There's no exception. An absolute value always has to output a positive. Will a positive number always be greater than -2 or greater than any other negative number? The answer is yes. So an absolute value is always going to be greater than a negative number for any value of m here. It doesn't matter whether m is a fraction, a decimal, the tiniest number that you can think of, or the biggest number that you can think of. It's always going to be bigger than a negative number when you take the absolute value of 10 minus m. So what does that mean for us? Well, the opposite of no solution. It means that everything is a solution, or all real numbers. And remember that you can abbreviate all real numbers with that funny looking R. So that is our solution, is that all real numbers are solutions. Let's look at one final example, and this is kind of one of those real world word problem examples. You're buying a new computer. The table shows the prices of computers in a store advertisement. You're willing to pay the mean price, so the average, with an absolute deviation of at most $100. We'll talk about what all that means in a second. We want to know how many of the computer prices meet this condition. So think about it. If you're wanting to buy a computer, you're probably not going to go to the store and buy the absolute cheapest computer that you can buy, because you're probably thinking, oh, I'm going to get what I pay for. It's going to be a piece of junk. On the other hand, you're probably not going to pay the most expensive price either, because you'll probably think that, oh, there's way too many bells and whistles that I'll never use. It's probably just overpriced for what I'm going to get. So you want to kind of hang out somewhere there in the middle. And so the middle in this case is somewhere within $100 of the average price of all these computers. So that's what absolute deviation means. We can deviate $100 one way or the other from our average. I want to remind you that we have a method of writing an absolute value equation, and we can use the same method to write an absolute value inequality. So remember that we have x minus the mean, or the average, also we called it the halfway point, was equal to the deviation, or that distance to the halfway point. So that's what we mean when we say deviation, is it's the distance from the mean to the high and low points. All right, so let's go ahead and take a look at this. So our mean in this case is going to be adding up all 10 computer prices and then dividing by the number of computer prices, or 10. So I cheated and had this written ahead of time. So the mean is adding up all those numbers and then dividing by 10. When you add up all of those numbers, you are going to get that the mean is equal to 6640 divided by the number of computers, 10. So we have $664 is the average or mean price. All right, so we can write our equation. We can say x minus the mean, which we just calculated, 664. And we want to be at most $100, absolute deviation of at most. So that means that we want to be $100 or less. We don't want to be more than $100. The most we want is $100. So that means that we will have a less than or equal to, because we're willing to spend not just $99, but $100 one way or another. So less than or equal to 100. That is going to be our equation. So since it's a less than equation, less than is an and. So let's go ahead and figure out what our biggest price and our smallest price can be. And we'll do that by solving this absolute value equation. It's already been isolated, so we can separate and solve. We'll say x minus 664 less than or equal to 100, x minus 664 greater than or equal to negative 100. So remember, we can go the opposite direction and be less than the mean or greater than that mean price by $100. We just don't want to be more than $100 off. All right, so let's go ahead and solve. We're going to add 664 to both sides, leaving us with x is less than or equal to 764. Remember, that's dollars. And then finally, the other one is adding 664 to both sides, giving us x is greater than or equal to $564. We can plot this just like we've done the others. Bigger numbers, but that's okay. $564, $764. And so we are somewhere in between those two numbers. We've got closed dot, and our x, the price that we're willing to pay, is somewhere in between. The last thing that we want to do, actually, let's go ahead and write our inequality first, and then we'll take a look at the final thing. So 564 less than or equal to x, less than or equal to $764. So we want to pay somewhere between those two prices. However, what the question actually asked is how many of the computer prices meet our condition of being between those two numbers. So let's just take a look. $890, too big. $650 is okay, so is $660. $240, too small. $725 is okay. $750 also okay, but that one's way too cheap. $670 is good, $650 is good, $825 is a little on the high side. So we have 1, 2, 3, 4, 5, 6. We have 6 computer prices that meet the condition. So we would take a look at those, compare all of the bells and whistles on them, and decide which one that we actually wanted to end up buying.